Hello everyone, I'm Yan Xia, now a postdoctoral researcher at the Technical University of Munich. I'm pleased to present our recent work, CASSPR, for single LiDAR scan-based place recognition. In autonomous driving, relocalization in a large-scale 3D map is a critical task, and place recognition is a key subtask of this problem. The aim is to recognize the place where a given scan is taken. We would like to input the scan into the search box and get its location from large geotagged database. So, to address this task, the common approach is to extract the descriptors from the database scans. Then, given a query scan, we retrieve the best match, and the recognition is performed as the nearest neighbor search in high-dimensional spaces. One challenge is that most previous descriptors have performed place recognition when given dense maps as a reference. While this is an important setting, accurate point cloud maps may not always be available in unfamiliar scenes and when an environment changes. Ideally, one would therefore prefer localization to be performed from sparse single-shot scans, which can be connected during normal online operation, instead of requiring a densely captured point cloud to be created first. One single LiDAR scan can cover an area between 160 and 200 meters in diameter, connecting a relatively sparse set of points. And the current SOTA voxel-based approaches nicely integrate spatial context across multiple scales. They do not exhibit the local precision of point-based methods. As a result, existing methods struggles with fine-grained matching of subtle geometric features in sparse single-shot LiDAR scans. So, our CASSPR includes three main contributions. We study the extreme sparsity of single LiDAR scans and propose a two-stage hierarchical cross-attention transformer module that is designed to compensate for the shortcomings of pointwise and voxelwise features, and then assess the computation and memory trade-off of the different approaches, finding that our method reduces inference time and memory consumption. Here is an overview of our CASSPR pipeline. The point branch captures the fine-grained geometrical features by using a simplification of a point net. The voxel branch performs convolution on sparse voxels in sphere coordinates. The point voxel feature fusion is achieved by a hierarchical cross-attention transformer module. And finally, lightweight self-attention units are used to encode the spatial relationship among local descriptors, followed by 3D convolutions and pooling. For the uneven density of points, a sphere voxelization method is introduced to balance the varied density of points in a LiDAR scan. Next, we quantize the point cloud with sphere coordinates into a number of voxels. Note that while the voxelization allows for robust 3D sparse convolutions, it necessarily loses many details from the point cloud. We can see about the 64% of the points are lost due to the voxelization. The first cross-attention transformer takes the sparse voxel features as the query and the pointwise features as the key and value. It extracts the pointwise features with reference to the sparse feature maps and outputs sparse tensors that are informed by the point features. Conversely, another cross-attention transformer produces improved pointwise features by taking the point features as the query and the sparse voxel features as the key and value. Finally, the aim of the third cross-attention transformer is to fuse both enhanced sparse tensors and enhanced pointwise features. The advantages of this strategy is to ensure that each branch is useful in isolation, thus preventing one branch from dominating over the other. Here are some results on the TOMB dataset. Given a scan as a query, here are the top 3 retrieved matches. The top 1 match has a very similar thing as the query. The right is the location of each point cloud in the reference map. For the query, we can see the location of the top 1 result is correctly overlapped with the query location. The quantitative results are shown here. The table shows our method achieved the highest retrieval success rate on the Oxford robot car and in-house datasets. Here, we also show the recall curves of the top 25 retrieval matches. Our CASSP outperforms the other approaches on the University of Sydney and TUM datasets, especially for the top 1 result. CASSP takes 29.7 milliseconds to encode one scan into a global descriptor with only 3.8 megabyte parameters. Although CASSP is a point voxel fusion architecture, it has lower trainable parameters compared with the pure point-based methods, including point-net flood, PCAN, and SOE-net. Here, we report the loop closure detection performance on the KT odometry benchmark. CASSP achieves the best performance, and only for average position on the sequence 000, our method is on par with LCD-net. Thanks a lot for your listening and attention. If you have any questions, feel free to contact me, and I'm looking forward to discussing and collaborating with you.